Okay, that's the first thing you have to know. So if we go back to our problem we had before, right? You will see this. Okay, so you'll see that our for this case stress X is equal to 0. Okay, now stress Z on the Z plane, right? This is not equal to 0. Why is that? Because there is a there is a normal stress is equal to 0, but shear stress is not equal to what? 0. Okay, but however, for this case, you can also carry out plane stress analysis. Okay, but don't worry about that. First, I'm just showing you example. Later on, when I show you more detailed analysis, it will be clearer to you. Right. So that is plane stress analysis. Now, the next thing that is difficult to acquire from textbook is what is in plane and out of plane. So in plane or out of plane, okay, so in plane is the plane drawn with the largest surface area. Okay, so like what do we mean by that? So again, I'm going to draw a very similar diagram like what we had before. So this is our X, Y, and over here our Z plane, right? So we construct the element over here. Right? So this first surface over here is our Y X plane, right? Over here, this is our Y Z plane, and over here, this is our X Z plane. So the XY, why I put YX? The XY plane is the largest, so it's the what? In plane. Okay, because largest area. Okay, and over here they are smaller, so they'll be your out of plane. Okay, and then this is also your out of plane. Okay, then let me do another view for you all to see, so that you'll be more sure of the definition. So again, the same transformation. Now we are going to draw the orientation this way now. Okay, now we're going to draw the orientation this way. So you will the plane is still the same. So this is still our XY plane. Over here, this is your YZ plane. And then this over here is your XZ plane. So now when you see them, you will know that the XZ plane is the largest, so this will be your in plane. Okay. This will be your out of plane. And over here, this is also your out of plane. So when you see questions, they ask you, can you analyze the stresses can you determine the maximum in plane or out of plane shear stresses? Okay, so it will be very clear. So if we were to look at some previous example that we did over here, like for this example, you can see now, right? You can see when we did this example, this is on week 8, Thursday, our last lecture. So this is our element A and our element B. All this, the biggest area that you see, right? These are all our in plane, right? And then this is also our in plane in element B. So in element A, the in plane is on your XZ plane. Okay. Whereas for element B is your YZ plane, as you can see. Okay. So we were already doing this, but I did not introduce the in plane or out plane yet. I did not want to confuse you. But as I mentioned, all of you have seen it before and know what it is before. Okay. So now it's just a matter of its definition. Okay. Any questions so far up to here? Are you okay? Anyone on the chat? If you're on the chat, let me know because I only have one computer with me now. Okay. Okay. Let me check the chat. Is everyone okay? Everyone seems to be okay for now. So we know what is plane stress analysis and what is in plane out. So next we are going to directly go into 2D Mohr circle. Okay. Now 2D Mohr circle is the fundamentals of Mohr circle. What I'm trying to say is if you know how to draw 2D Mohr circle, right, you apply the same principle in constructing 3D Mohr circle. Okay, there's nothing new. Okay, that is the good thing. Okay, so you have to grasp the fundamentals first. Okay, so now let's draw an element. So now you all know what's an element. Okay, so let's draw that. So we're going to do 2D. So this will be your X, and this is your Y, and then we're going to have our element. Okay, so this is our element. So on the element, we are going to see the stresses. Okay, so over here you have a stress of 40 megapascal. Then you have over here 20 megapascal, and then you have a shear of 30 megapascal. Okay, so that's your Mohr circle, and now you will know why is it 40, 20, and 30. Yes or no? This is based on the loading condition that I taught in the last lecture, right? Or the one we just finished. Okay. So we have this sort of stress value. Okay. So what we are going to find now is we are going to determine the principal or we are going to find so we're going to find a few things. The average stress, and I'll write this down. Sometimes you see this in questions, average in plane stress, okay, or normal stress. B, you're going to find the maximum in plane shear stress, we are going to find the principal stress or stresses, and then you're going to find the principal plane orientation, and then we are going to construct the element at its principal plane. Okay, right. So if you look at the stresses, I know all of you are familiar with normal stress. So we know that stress X is equal to minus 40 megapascal. Stress Y is equal to positive 20 megapascal, right? So what you can see over here, if the arrow is pointing towards the element, this is what we call compression. And then when it's pointing away, like this case, right, is going to be in tensor, away from the surface, as you can see now. Okay. Now the shear we have, right, the shear XY is going to be equal to the shear YX. And this is equal to positive 30 megapascal. Okay. So you will see like Y 30 megapascal. Y, not Y positive 30 megapascal. Okay. So I'm going to show you what do we mean by positive shear and negative shear. Okay. So I'm on over here, I'm going to have positive shear. Okay. So positive shear, this over here is our element. Okay. At the center is our origin. So this is our Y. This is our X. So over here, this is our shear stress. Right. The intersecting plane is X. The shear force is acting Y direction. And over here, this is shear Y X. Okay. So if you if in terms of if we were to look at you have to complete the element. Okay, you have to draw the opposite end. It will look like this. Okay. So we define this orientation as positive shear. Why is that? Okay. So over here, I'm going to, so this surface, I'm going to use a different color now. This surface over here, right, is a X positive surface, right? Because it intersect the X where the axis is on the or the plane is on the right hand side of the dot of the center. Okay, so this surface over here is a Y positive surface. Okay, and the arrow is going up, so is Y direction, the shear or the shear in Y. So it's going up is what? Positive. I just put positive, right? And then the shear over here in terms of X is also positive because it's going up. And then if we look at the other surface over here, right? this is our X negative surface, right? Because it's on this side, on the left-hand side of the dot in the center, right? And this will be our Y negative surface. And if you look at the shear stress, the shear in the X is also in the negative direction. The shear in the Y, okay, the shear in the Y is also negative, right? So what I'm trying to say is positive multiplied by positive is positive. Positive multiplied by positive is positive. Negative multiplied by negative is positive. Negative multiplied by negative is positive. So this is why this is called positive shear. So if you look at how the positive shear, the element deform, right? The element will deform this way. I'm going to draw the deformation pattern now. So this is our deformation pattern. Okay. So how I get that definition pattern is these two arrow over there. If let's say the square is like a rubber band, if you squeeze them and stretch, right, you will have that sort of definition pattern. Okay, so this is again the definition pattern for positive shear. Okay. Then the next thing we are going to look at, okay, negative shear explanation will be really quick. What I propose is that we take a 5 minutes break, we come back, we do negative shear. Okay, I'm going to stop.